Hello, in today's video, we discuss what can a spectrum analyzer really measures. It's not just for frequency measuring. You can do much more, such as channel power measurement, adjacent channel leakage measurement, and then this is the comparison between this traditional spectrum analyzer and then a modular software-defined RF spectrum analyzer. In the early days, the spectrum analyzer is only the traditional one. That means you buy the whole units with the monitor, with the user interface here. And then now you can have the so-called modular software-defined spectrum analyzer. That means you only purchase some of the hardware, the PX, for example, a PXI module, which you can get from Keysight or National Instrument or other vendor, maybe such as MVIT technologies. So then you install the software in your computer. You connect this kind of PXI module to your computer. You can do a lot of measurements, such as the spectrum analysis, which includes the frequency, the channel power, adjacent channel power, the IoT, and then the sum of SSDF. We will go to all details later. And then you also can do a vector signal analysis. And of course, this is not a spectrum analyzer anymore. It should be a signal analyzer. But anyway, this concept, spectral analyzer and then signal analyzer, is exchangeable. And then you also can even customize your measurement. You maybe, for example, you can reach the source code. You can even change a little bit of the software installed on your computer. And in this video, we only discuss the spectrum analysis. We're not going to discuss the signal analysis. If I can loan these units from my friends later, I may be prepare another video to discuss the signal analysis. So basically, this is the spectrum analyzer discussion for today's video. And this is a traditional spectrum analyzer. I see all these frequency components here, and each frequency that we are reading here, all this for the power of each frequency components. And then this is the user interface. And then this one is a modular software-defined RF spectrum analyzer. This is the so-called PXI modules. As I just mentioned, you can find this one from Keysight, NI, or other vendors. And this one actually is a screenshot from the one of the computer, and which installed the software. And you can see this user interface is quite similar between this software-defined spectrum analyzer and the traditional one. And this is the menu here, and here is the display window, and these are the soft keys, and this is the control buttons here, and this is the device configuration and the measurement display area. And here is the keypad and the knob, and this is the status bar. We will find some of more details later. So okay, this is basically a spectrum analyzer does for frequency domain measurement. For example, I have a few marks here, 1, 2, 3. Then measure the different power at the different frequency. So if you are very familiar with this one, and then I think we can just skip here, don't discuss too much, because this is most of the case we use spectrum analyzer, we use this function. And then we are going to discuss the other functions of spectrum analyzer. First, let's discuss the spectrum analyzer measure the assigned channel power. Okay, have some of ideas. For example, in LTE, one of the channel is occupied, assigned 10 megahertz. So this is the signal generator. Generate the power. The power level is minus 40 dBm in 10 megahertz bandwidth. So this one I connected the signal generator to a short jumper cable to the input port of the spectrum analyzer, the PXI port, input port. Then we measure the bandwidth. Okay, this way is 10 megahertz because this is assigned one. How much power in this 10 megahertz is minus 40.4 dBm, because the signal generator generate minus 40 dBm plus the cable loss 0.4 dB. So here displays the channel power. The assigned channel power in 10 megahertz is minus 40.4 dBm. This is a function of measure the assigned channel power. So for what is assigned channel power, if you are in the telco industry, you should be very familiar. Today we are not going to discuss the details of these techniques related to LTE. We just discuss the spectrum analyzer capability of measurement. Okay. So this is the spectrum analyzer to measure the assigned channel power. And then the next one is use the spectrum analyzer to measure the occupied bandwidth. So for occupied bandwidth, you can define the bandwidth by yourself. For example, you say my occupied bandwidth supposed to be with 99% of the assigned channel power. Remember just now we say the assigned channel is 10 megahertz. The power is minus 40.4 dBm. So I need 99% of this one. What is the frequency band here? It's 8.93 something megahertz. So this is the occupied bandwidth. But if you change the definition of the occupied bandwidth, for example, you want the 99.5% of assigned channel power, then the occupied channel bandwidth will slightly wider. See, here is 8.93, here is 8.97. So this is how we measure the occupied bandwidth. All this percentage is configurable in the user interface. For example, here you can click here and then you change the percentage here. You can even put a 98% or something other value you like. And then this one is we use the spectrum analyzer measure the adjacent channel power. Again, this is different standard, different regulations. They have different requirements. For example, the most common one is we measure the immediately adjacent channel power. For example, this one, the channel is still 10 megahertz. So each adjacent channel is 10 megahertz. We measure this, the orange color at both sides, and then the value is here, the channel power. The left channel is minus 84.76 dBm, so which is minus 44.54 dBc compared to the carrier. That means it's 44.54 dB lower than the carrier power. This one, the right side, which is minus 85.79 dBm, so it's minus 45.56 dBc compared to the carrier. And then similarly to this green color, the left side and the right side value, then the dBc of course is even lower compared to the carrier. The C is the carrier here, and this is the just measure the immediately adjacent channel, and then this one is measure the defined adjacent channel. For example, if we are doing LTE, you need to apply the this to against the 3GPP standard. So this one, for example, you have the the carrier here, and then you measure the channel power. You define the offset is start from here, and then the bandwidth is 100 kilohertz. How much power this is? One, you measured. And then for the green one also, you offset the center here 600 kilohertz. The bandwidth you measure is 100 kilohertz. Then the power is that much. So this is two types of adjacent channel measurement. Anyway, today's video we are not discussing how we conduct the measure. We only show the capability of the spectrum analyzer. So you just understand the spectrum analyzer can measure the channel power, they assign the channel power, the occupied bandwidth, the adjacent channel power or adjacent channel leakage ratio here. How to measure it is then you need to do some of the study, or we need to prepare a different video. But that one I need the hardware plus the software. I cannot just do it based on the screenshot here. And then the next one, we are going to measure the third order intercept, the TOI. Before that, we need to have some of ideas of what is the TOI. For example, if we have two frequency F1 and F2, both are in the passband filter. See? So there is the products 2F1 minus F2 and 2F2 minus F1. These two all fall in the band path of the filter, so it's harmful because this one you cannot filter out. But for others, this second order F2 minus F1 or 2F1 F2 plus F1 to F2, all these are out of the filter, so can be filtered out. It's not harmful. And this one also, this is still third order intercept, but this one is far away from the passband, so it's not harmful. So the only harmful is these two. So in based on this concept, we can see the TOI here. This is a screenshot. I put two tone. The lower tone is minus 250 kilohertz. The upper tone is 250 kilohertz. The center frequency is 2 gigahertz. So these two put together into the receiver, then the TOI at both sides is here. The value is here. Okay, the value is here. And then how this value comes out, you cannot directly get from here. So I prepared the slide to list down the formula and that calculation there. Next one here. So for two-tone set, output default TOI is this, calculate this way. So all these details calculate here. So minus 16.13 dBm minus 16.01 dBm match here. Match here. So again, this is only show the capability of the spectrum analyzer. What spectrum analyzer can measure. Okay, this is the TOI, and then this is another one. We seldom use it, but once in a while we maybe need to conduct this test. The spectrum analyzer can measure the complementary cumulative distribution function, the so-called CCDF. And then you can read the value here. Okay, this red line actually is a reference line. It's a reference curve. It's a band limit Gaussian noise CCDF reference line. So all this is the white curve here is the real value, real measured result. So if you see, look at it here. Let's look at this one. 0. The 0 is average power marked as 0 dB. This because everything here is compared to the average power. So average power, of course, is 0 dB higher than itself. So 0 is 0 dB. and here you can see it's around minus 11 something. Okay, this one is 11.2 dB. What that means is the peak power is 11.2 dB higher than the average power, because it dropped here. And then this one, 10%, this one, you see that this is 10. We draw a line from 10 cross here, and here is 4 dB. What that means, 10% time the power is 4 dB higher than the average power. And then some other values here, this average power percentage 35.99. what that means, 35.99% of the time the power is not higher than the average power. And here still some more value, it's 0.0001% power. The time the power is 11.2 dB higher than the average power. So that means even though the peak power is 11.2 dB higher than the average power, but there's still a little bit percent of time the power is 11.2 dB higher than the average power. And then this is the one of the function of the spectrum analyzer. Measure the CCDF. The value is here, and if you are not using it at the moment, you maybe just keep it, and later if you want to read the value, or you want to understand what the value means, you can refer to here. This is almost list down all the values we need to read here. And then here is the spectrum analyzer can measure the spurious emission. So we put the mask here, mask all here, and this is the mask here, and this is the absolute value, this is a relative value. So you can set, for example, you set the start frequency 5 megahertz. That means 5 megahertz away from the center frequency. You start from here, 5 megahertz. Then the stop frequency is 7 megahertz. Here is 7 megahertz. Same for both sides. Here is 5, 7. Then the RBW all is put in 1 kilohertz. Similarly for other points, from 7 to 9, 7 to 9, 9 to 11, 9 to 11, then 11 to 13, 11 to 13, and then I put another one, 13 to 14 at both sides. So you should set this value. You set this value based on the requirement. Then your carrier power shouldn't exceed this mark here. So this is the mask. Basically, you cannot your value cannot higher than that. So this is one of the function very important for spectrum analyzer, because for the especially for some of the RF products, your input to some country, you need to conduct the so-called acceptance test. Then this is one of the important one, you have to conduct the test. So this is all for today's discussion. If you need more discuss on spectrum analyzer, please leave your comments. And if you like this video, please subscribe, share, and like. Thank you.